Hello. Today, I'm going to use the gradient to compute the directional derivative of a real valued function of three variables. In other words, the function f mapping R3 to R, defined by f of x, y, z is yx plus z squared. Find the directional derivative of that function at the point 2, 3, 1 in the direction of a vector making an angle of 2 pi over 3 with the gradient of f at that point. Okay, that's a long sentence. So they're asking for the directional derivative of f in the u hat direction at that point. So we would actually, in the class, I've been writing that differently. I would call this the directional derivative in the u hat direction of f at the point 2, 3, 1. So the directional derivative of f, the point 2, 3, 1 in the u hat direction. And we're not given exactly what u is, but we're given everything we need to know. U hat is a unit vector. And it's also makes an angle of 2 pi over 3 with the gradient. And the way we compute this is we take the gradient of f at the point 2, 3, 1. That's a vector. We dot it with the unit vector in the direction, taking the directional derivative with respect to. Okay. Now, if we had the components of this, we can find the components of that, but we don't really have the components of u. So we better go use this formula for the dot product of one vector with another is the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them, right? So that's going to be the magnitude of the gradient of f at the point 2, 3, 1 times the magnitude of u hat times cosine of the angle between them. Okay, well, the easy part is that the magnitude of any unit vector is 1. That's the definition of a unit vector. Vector with magnitude 1. And then what about theta, cosine theta? Well, they tell us that theta is 2 pi over 3. Okay. And if I think about the little unit circle, since the angle is bigger than pi over 2, it's not an acute angle, it's probably best to think about the unit circle here. This is the angle, 2 pi over 3, a third of a full circle. So it's a little bit higher than it is to the left. And so I know that like this square root of 3 is coming in here. So this is negative a half. Square root of 3 over 2 are the x and y components of that point. Okay, the y component is a little bit bigger than the magnitude of the x component. Cosine is the x component. So cosine of theta, or 2 pi over 3, is negative a half. Right? So this thing here is negative a half. And all I need is this number here, the magnitude of the gradient of f. All right. Well, gradient of f at any point, which we need to do before we find gradient of f at the point 2, 3, 1, gradient of f at any point is the vector. I take the partial derivative with respect to x as the first component. That's y. Partial derivative with respect to y, that's x. Partial derivative of f with respect to z is 2z. Okay, so that means that the gradient of f at the point 2, 3, 1 is going to be, right, remember, the y is the 3, x is 2, z is 1. So that's 2. So the gradient of f 2, 3, 1 is that, but its magnitude is the square root of the sum of the squares of the components. That's 3 squared plus 2 squared plus 2 squared. That's square root of 9 plus 4 plus 4, 9 plus 8. That's square root of 17. Okay, so this number is square root of 17. So it's, the answer is square root of 17 times 1 times negative a half. Okay, we probably want to simplify that. That's just negative square root of 17 over 2. All right, that's all there is to it. Might be a good time to mention that this formula, the directional derivative after the point in the u direction, always has a similar form. It's the magnitude of the gradient times 1, it's always 1, times cosine of the angle. So the biggest the directional derivative can ever get is if the direction is in the direction of grad f, in other words, theta is 0. Cos of 0 is 1. So the biggest of the directional derivatives can ever get is the magnitude of the gradient. The smallest the directional derivatives can ever get is the negative of the magnitude of the gradient. When theta is pi, or 180 degrees, and the cosine of theta is -1. Okay. And if you take the directional derivative in a direction perpendicular to the gradient, the directional derivative is 0. Right? So you're walking around a hill, you can either walk uphill, that's the fastest you can go uphill, you can walk downhill and your elevation is decreasing as fast as possible, or you can go sideways and then your elevation stays the same. Okay. All right. Bye. Have fun with this web work set.